So hello together. Today I want to talk about a special problem. This problem is how to use the Smith chart for impedances to deal with admittances. And we will do this with a little example. So this example is part of exercise 1, problem 3. Here it's written, determine with the help of the Smith chart the absolute value and the phase of the reflection coefficient when a transmission line with characteristic impedance of 50 ohm is terminated by the parallel connection of a resistor and a capacitor. So to solve this problem, here we have a parallel connection, so it's always of advantage to deal with admittances. But if I want to deal with admittances, then I must talk about how to use our Smith chart, which is a Smith chart for impedances. And our Smith chart for impedances is a result of the formal mapping of the Z-plane onto the R-plane. For the normalized admittance, which is Y is 1 over Z, we get the following mapping, which results, of course, in a different chart. We would have R is now 1 minus Y divided by 1 plus Y. Of course, this conformal mapping is different to this conformal mapping. But by introducing a minus 1 in front of this mapping, we come to the same mapping. We have here the same mapping for between Z, and here is the mapping of the Y-plane, but with the only difference that if we want to read out the reflection coefficient, as I have to multiply with minus 1. What does this mean? The last equation tells us we can use our Smith chart for impedances also for admittances, but if I want to read out the reflection coefficient, we must mirror the admittance at the center of the Smith chart. So this we will demonstrate now with in our example. As I already told you, we have a parallel connection. As soon as you have a parallel connection, it's of advantage to use admittances. Our load impedance is a parallel connection of a resistor of R 25 ohm and C 3 picofarad at a frequency of 2.12 gigahertz. So if I calculate the load admittance, I must use this equation 1 over R plus J omega C. If I insert our numbers, this would result in a normalized admittance 0.04 plus J 0.04. Sorry, here's the J missing. But if I now normalize the load admittance, we get the small y will be the capital Y divided by YC, the characteristic admittance of the transmission line, which will be YL times ZC. And this will result now in 2 plus J2. So in the first step, we can draw now our normalized admittance in our Smith chart. So here we have our Smith chart, and we have the value 2 plus J2, which means I have to find the real part circle of 2 and the imaginary side circle of 2, and at the intersection point we will have 2 plus J2, so this is just the blue dot here in the Smith chart. As a result, we can say we are now in the admittance plane. But since our Smith chart is a Smith chart for impedances, we may not read out the reflection coefficient. Normally the reflection coefficient would be given as an error from the center of the Smith chart to this point. But since we draw in an admittance, we are now in the admittance plane, and we may not read out the reflection coefficient there because of the minus 1 I sketched before. So what do we have to do? To read out the reflection coefficient, we must mirror the admittance at the point 1 of the Smith chart. So we have here the point 1 in the Smith chart, and now we mirror this blue point into the red point here, which is just a straight line from blue point through the 1 to the red point, and the length can be evaluated using a compass, for example. So then we get this point here, the red point, and now we are again in the impedance plane and can read out the reflection coefficient. So the reflection coefficient, the absolute value, is given from the length of the red line here, which also can be figured out using a compass. You have to take this red line into the compass, and then you can use the button scale here, the scale at the bottom, to figure out the absolute value. To figure out the angle, we must always measure the angle with reference to this line here. So the red circle gives you the angle. And so we can read out a value now of round about 0.62 times the exponential function minus j 150 degrees. But what does this mean in the conclusion? We can use our Smith chart for impedances also for admittances. If we draw in an impedance, we are in the impedance plane. If we draw in an admittance, we are in the admittance plane. If we draw in an impedance, we are in the impedance plane. We can switch between the two planes by mirroring at the point 1. Here is the mirror point. And the reflection coefficient may only be read out from the impedance plane.